Good morning and welcome. We are in our third lecture, T1101, Electrical Engineering Circuit Analysis, the course that is done by engineering students at NAST. And today we are going to look at parallel circuits and Kirchhoff's laws. That's our fourth lecture, but on Zoom that should be our third lecture, I'm sure. Right, so I will be hosting you, Engineer Gunda, Electronic Engineering Department. So, when you look at parallel circuits, by looking at a network, can you mute your audios as soon as you join the class, please? Otherwise, it will be difficult for us to proceed. Can you mute your audios as soon as you join the class? Thank you. So, for us to identify a parallel circuit, all we have to notice is that if there is a parallel network, then there should be two common points between the networks or between the elements. So if two networks have two common points, then they are in parallel, or if two components have two common points, they are in parallel. So that's how we identify a parallel network, right? So the characteristic of parallel networks is that they have the same voltage across them. That means the voltage that we measure across any two components that are in parallel should be the same. And any common point in a circuit is referred to as a node. You realize the importance of identifying nodes as we move on. So if you look at that circuit given in the diagram, you realize that this is one node and this is another node. And these two nodes, they are common to both R1 and R2. So if R1 and R2 share two common nodes, then they are in parallel. But then if you extend it to the source, you realize that the source also is on node A. Remember, any line in a circuit is taken to be a short circuit. That is, in practice, we would say it's just a connecting wire. So if two components are in parallel, then they have the same voltage across them, meaning to say the voltage across R1 and the voltage across R2 is equal to V, because V is also in parallel with the two resistors. So R1 and R2 are in parallel, they share node A and node B. Voltage R1 equals voltage at R2, right, which is called V, which is the supply voltage. Then current branches at the nodes. So what do we mean when we say current branches at the node? We are saying the current coming from the source is current I. As it reaches this point, it branches into this branch, and the other current goes into the other branch. So once you get at a node, you should know that the currents will branch. But now when the currents come to this node now, they will again combine at this point to form the source current. So that should be known. So if you have two resistors that are in parallel, just like we did with resistors in series, you can still combine them, right? In other words, there is always an equivalent resistance that can be taken across any resistors. Right? So if you have those resistors, R1, R2, up to any resistor RL, they can be taken to be an equivalent resistance R total. Now, for you to calculate R total, 1 over R total should be equal to 1 over R1 plus 1 over R2 plus 1 over R3 up to 1 over Rn. And then if R1 is called R2 up to Rn and it's called R, then the total resistance is called R over N. What it means is if you have the same value of resistances connected in parallel, their total equivalent resistance as observed from this side will be equal to the value of one resistor divided by the number of resistors that are in parallel. That's how you calculate the resistance of a parallel network. So for two resistors now, in parallel, let's say resistor R1 and R2, 1 over RT, so RT will be the resistance observed from this side. So this will be your R RT. So RT now, we will say 1 over RT should be equal to 1 over R1 plus 1 over R2. Then if you put them under the common denominator, primary school mathematics, you are now saying 1 over RT is equal to R2 plus R1 over R2, R1. And making RT the subject, you realize that RT is equal to R1, R2 over R1 plus R2. So for any two resistors that are in parallel, the total resistance is called their product over their sum. That's simple. That is for two resistors. Remember, it's only for two resistors. If there are more than two, then you have to use the usual 1 over R3 going on like that. Then you can calculate the resistance. But now, if you observe, 1 over RT is actually equal to 1 over GT. Remember, I talked about conductance. So that would be 1 over GT. And 1 over R1, 1 over RT is equal to GT. And 1 over R1 is equal to G1. 1 over R2 is equal to G2, and so on and so on. So you realize that the total conductance of elements in parallel is given by the sum of the conductances. GT will be equal to G1 plus G2 plus G3 plus G4 up to Gn. But then if G1 is equal to that up to G, then GT will be equal to the number of conductances in parallel multiplied by the conductance of a single resistance. So you can still move from this point to that point, or from that point to that point, by making those observations that G is equal to 1 over RT, right? An example, determine the total resistance and conductance of the circuit shown. So in that circuit, you realize that we have two resistors in parallel, 3 and 6, right? And we want to calculate the total resistance and the total conductance. So remembering that RT is called R1 over R2 plus R1 over R3 for two resistors in parallel, then RT is equal to 2 ohms. Then conductance is called 1 over RT, which means conductance GT will be equal to 0.5 Siemens, which is the unit of conductance as observed in the previous lecture. Second example, determine the total resistance and conductance of the circuit shown. So that circuit, again, you remember we said if components share two common nodes, they are in parallel. So regardless of the triangular shape in which they are arranged, they still share common nodes. We can say node A and node B. So in reality, their resistance will still be calculated as usual. But for some of us who want to have a sort of a photographic memory where you remember the way you saw things previously, you can still redraw and extend this point so that it becomes straight. Then you can also realize that again, we still at point A and point B, and R1, R2, and R3 are still in parallel. So these two is the same circuit that you are observing there. So you can now write, if you know the resistance there, you can write the conductances. So R1, G1 becomes what? 1 over 2, 0.5. G2, 1 over 4, 0.25. G3, 1 over 5, 0.2 Siemens. Then from what we know that GT is called G1 plus G2 plus G3, then you can say GT is called 0.95 by just adding these three conductances. Using those three conductances, you can now say RT is called 1 over GT, both the inverses, and you get 1.053 ohms as your total resistance. So it is easier to use conductances to get resistance for parallel networks than to use resistances. But at the same time, you can still use 1 over RT is called 1 over 2 plus 1 over 4 plus 1 over that. Still, making RT the subject, you still get the same answer. So that's an example of a parallel circuit. Now, we said when current enters a node, it branches through the two points. So what are we saying? We're now saying there should be a law that is used to calculate the current entering a node after it is divided. So in that case, IS is coming to node A, it branches to form I1, and it also branches to form I2. So I want to see how then can we calculate the voltage, the current I1 and the current I2, knowing IS and the two other resistance, right? So the voltage across each element is equal to E. So from Ohm's law, I1 is equal to V1 over R1. Remember, V1 is also equal to E. Then I1 is equal to E over R1. I2 is equal to V2 over R2. Remembering that V2 again is equal to IE because they are in parallel. Then I2 is equal to E over R2. So taking the resistance equation and multiplying both sides by the supply voltage E, we know that E over RT is equal to E over R1 plus E over R2, which implies that IS, which is the total current, should be equal to current I1 plus current I2. So we said this current is now IS is equal to the sum of this and that, because they are just branching in those two networks. So we can conclude that for a single supply, the total source current equals the sum of the branch currents. So the magnitude of the current in each branch is determined by the resistance of that branch. And it can be shown that the current I1 will be given by R2 over the sum of R1 plus R2 and R2 multiplied by the supply current, right? You can work around to see the proof there. So it is good practice to use this formula by combining resistance and remaining with one for which you want to calculate the current. In other words, we are saying if you had any other resistances, this is a simple formula to remember. So you just pick the branch in which you want to calculate the current, then you bunch up everything that is not in that branch into a single resistance, then you use the formula to calculate the branch current. Or you can calculate by first calculating the total parallel resistance RT, then the current in branch X, which is IX, will be equal to the total parallel resistance RT over the resistance of branch X multiplied by the supply current. We'll show that by way of an example. Right. For example, for the circuit given below, calculate the total resistance, the total current, and the current through each resistor. So that is our circuit with the supply voltage of 27 volts, 9 ohms R1, 18 ohms R2. We want to calculate the total current supplied from the source, which is IS, and also the current through each resistor, that is I1 and I2. So how do we do that? There are many ways, but I'll show you one of the ways which you can use. So first, the total resistance of this network is required so that we can use V is equal to IR, Ohm's law, to calculate the total current. And so that product over sum, that's 9 times 18 over 9 plus 18, and you get your 6 ohms. Then the total current, IS, will now be equal to the supply current divided by the total resistance, RT, and you get your 4.5 amps. So this is 4.5 amps, right? Then using Ohm's law, I1 with the current here is called the voltage across R1 over the resistance of R1, which is 27 over 9, which is 3 amps. Then I2, again, is 27 divided by the resistance of the branch, which is 18, and you get to 1.5. Then you can observe that IS now is called I1 plus I2. This is our IS, and that's called the sum of this and that. Right. But again, you can use the current divider rule to calculate that. Once you get IS, you can now say 18 over 27 multiplied by IS, you get current here, and 9 over that is just current here. Now, if you observe, you realize that in a parallel network, the value of the resistance through the network is inversely proportional to that resistance. How do we determine that? If you go back to our previous equation, you can see an inverse relationship between current and the resistance. So current I1 now, right, is given by the value of R2 over the total resistance. But if you come to this other formula, you'll see that your resistance of the network is in the denominator, which means the current is inversely proportional to the resistance, which means a high resistance branch will have a lower current, and a lower resistance branch will have a high current, because current, you remember, it flows in the path of minimum resistance or of least resistance. Then we go on to what is called Kirchhoff's current law. Current entering a node should be equal to current leaving a node. That is the law. So in other words, we are saying the algebraic sum of currents at a node should be equal to 0. Right? So current entering is equal to current leaving the node. Can you mute your audio, please? Right. So what we are saying is we have a node here, which is marked in that blue, the circle, and branches are coming into that and others are leaving. So what we are saying by Kirchhoff's current law is that the currents leaving this node, that is I5 and I4, should be equal to the sum of the currents entering the node, so that there is no accumulation of charge on the node. So whatever current enters should be the current leaving. In other words, you can say I1 plus I2 plus I3 plus minus 5 and minus 6, because this is subtracting current from the node, we took it as negative. So that should be equal to 0. That's the simple current law. So for example, given that circuit, calculate I0. So I0 is actually leaving. So current entering the node should be equal to current leaving. So what currents are entering? It's 2 and 4. So 2 plus 4 amps should be equal to 10 plus I0. Then I0 becomes equal to minus 4 amps. So what does that imply? It implies that the current is actually flowing in an opposite direction. Remember when we talked about currents in the first lecture, we said current is a vector quantity. It has both magnitude and direction. So if you say I0 is equal to minus 4 amps, we are saying in the actual fact, I0 is entering the node. That's the implication of a negative sign when you calculate your current. So whenever you calculate current and you get a negative sign, what it is telling you is that the current is flowing in an opposite direction to the one which you gave it in your calculations. It doesn't mean that it's a wrong answer, but it simply means that the assumed direction is opposite the actual direction. That's all. Then, here we're talking about parallel circuits and we talked about series circuits. But now you realize that in electric circuits, you don't have a purely series circuit or a purely parallel circuit in reality, that is in practice. So as a result, you realize that you have to combine a series and a parallel circuit to form what we call series parallel networks or series parallel circuits. In other words, we are saying some components will be in series and others will be in parallel. For example, that circuit is a series parallel network. So let's identify components in series. These two are in series because they share one common point. But when you come to this point, you will notice that this combination is actually in parallel with this and is also in parallel with that. And this whole combination, if you make it a resistance, let's say R1, then R1 is now in series with the 8 ohm resistor because now they share two common points and so on. So that's how you will be analyzing those circuits. Simplify any part which you see is in parallel or is in series. So from here, you can realize that the 10 ohm and the 20 ohm, they share two common points. So these two are now in parallel. You can combine them using any other laws that you use. So these are some of the circuits that you will meet now in practice, where you have to be able to simplify that circuit using series parallel network solutions. Right. For example, determine the total resistance between A and B. So when we talk about resistance between A and B, we are saying the resistance that a current coming into here and leaving that, the resistance that it will meet in its path will be the total resistance between the 2 points, right? So what are we saying? We are saying the current, when it comes here, some of it branches at this point, the other passes there, the other one branches, and the other branches there, and the other one passes there, branches there, branches there, the other one passes there, right? When it branches there, it combines here into another current. Then this one will also combine with this into another current. Then this one coming there will combine with that and into another current. Then the one which branches there combines with this one into another current. This one will combine into another current, and it lives like that. So this current, if it is I, this current is also equal to I. The current that entered the circuit should be the same current that leaves the circuit. Okay? So I want to calculate the total resistance. So how do we go about this? I'll try to be slow in this one so that we understand. So the first thing that you do is identify components that are in series and combine them. The reason why I chose components in series is because the components in series are easy to combine. You just add them, right? For parallel components, you need a longer calculation. So it's very advisable to first check which ones are in series first. So if you observe, we'll realize that the 9 ohm resistor is in series with the 11 ohm resistor. Therefore, the total resistance of the combination, which I called RT1, is equal to 20 ohms. After that, you redraw the circuit with RT1. So this is now your RT1. We have a new circuit now. Then we look for components that are in series. You observe that there are no more components in series. Then you identify components that are in parallel. From there, you realize that the 5 ohm resistor and the 20 ohm resistor, which is RT1, are now in parallel. So you combine this and that. The two product over sum, their product is 100, their sum is 25. So RT2 is called 4 ohms, right? So this is now RT2. So if you also find other components in parallel, you realize that the 20 and the 10 ohm are also in parallel. Then product over sum, that's 200 over 30, that's 20 over 3, and your RT3 is about 6.6667 ohms. It's better if it's in an intermediate calculation, you write the fraction, it's more accurate, or you maintain up to 5 decimal places for intermediate calculation so that you don't lose accuracy. Then after that, you redraw the circuit with RT1 and R2, T2. So that is our RT1. That is our RT2. That is our RT3. Then you proceed. Again, look for components in series, no components in series. Find components in parallel, you find them. The 4 ohm and the 4 ohm are in parallel. Remember, I said if two resistors of equal value are in parallel, then their result is equal to the resistance of 1 divided by the number of resistors. In this case, it's 4, and the number of resistors is 2. So you have your RT3 is equal to 2 ohms, right? So you have your RT3 there. Then this now will be in series with the 8. So if you combine this into one resistor, to be in series with 8, then RT4 becomes equal to 10 ohms, right? Sometimes you can just write the statements without redrawing. If you know you are accurate, you can write the statements and still go on. But if you want to verify, I'd also advise you to what? To just redraw. It's also advisable. So here we are now redrawing with our 10 ohm and that in parallel. Then we combine those two, you get your 4 ohms there. Then the 4 ohms will now be in series with the 6 ohms. You get your 10 ohms as a result, right? So you now have your 10 ohms here, and then this remaining. Now you see that the 15 and the 10 are now in parallel. So you combine them, right? And you get your 6 ohms. Then after that, you realize that those combinations will now form about 3 resistors, one there, another one there, and another one there. And you have your points A and B. Now they will be in series, and you add them, you get your 15 ohms as the total number of, the total resistance of the circuit. For the circuit shown, calculate I4 and V2, right? Again, you determine the total resistance RT of the circuit, right? How do you determine the total resistance? These two are in parallel, you combine them, then they will be in series with that. So this combined is 2, this is 4, so it becomes 6 in parallel with 8, and you get your 24/7 ohms. Total current now becomes IS, becomes called the voltage over the total resistance, you get your 3.5 amps. Then using the current divider rule, this is 6, this is 8. So I4 becomes equal to what? Becomes equal to 6 over 14 multiplied by 3.5. That will be your I8, right? Or using Ohm's law, I4 will be what? Is this 12? I4 will be equal to 12 over 8. So you choose what to use. You can use the current divider rule, or you can use the Ohm's law. This is a voltage 12, this is a node, this is a node. So I4, even without calculating the total resistance, you could just straight away say I4 is equal to source 12 over resistance. You still get your 1.5. So this is the longer solution. You can just use that one, right? Then the current through branch R1, current here, now you want to calculate the voltage V2. The current through R1 is equal to 2 amps. Remember, our total supply is 3.5. This is 1.5, so this is 2 left getting into there. Then the voltage across V2, that is this voltage V2, is the voltage across the parallel combination. So you combine the 3 and the 6 into one resistor, that is 2. Then you use the voltage divider rule. The voltage from here to there is 12. Then the voltage across the 2 is 2 over 6 multiplied by 12. 2 over 6 multiplied by 12, and you still get your 4 volts. Or the current in that combination will still be equal to 2 amps getting in there, and still you get your 4 volts. So you can use any other method that you want to get the total resistance and the total voltage across there. Right, so you can also determine the current indicated in that circuit, right? I'm running out of time. I think I will be fast enough to do that. So simply simplify the circuit until you are left with branches for which you want to calculate the currents, right? So in that case, we have this branch, and we have that branch. So we can combine anything else and try to leave those branches intact, because we want to make calculations for those branches. So R1, R2, and R3, they are in series, therefore the R total is 24 ohms. Then that R total is now in parallel with 24, and you get your 12 ohms. Then the RT is now in series with R5, so it's now 12 plus 12, you get your 24 ohms. So the left side of the source is now 24 ohms total. You redraw the circuit with that. Then after that, you go to the right. Remember, I said our branches of interest are this, that, and that. So what it means is we can combine R8 and R6 so that we get our 9 ohms there, right? You draw the circuit, you have a 9 ohm there, right? Now the 9 ohm and the 9 ohm are in parallel. since you want to calculate the voltage, there is no harm in combining these two because since they're in parallel, they still have the same voltage across them. So 9 and 9 in parallel is 9 over 2, you get your 4.5 there. And then it's now in series with 12 kilo ohms, and you get your 16.5 kilo ohms is that. So you now have two branches, one with 24 ohms and the other one with 16.5 kilo ohms. Then the other total, if you check on these two nodes, you realize that this side and that side, they share the same node, which means this side is actually in parallel with that side. So it means 24 is now in parallel with 16.5, and we get to 9.778 kilo ohms. That means the total supply current from the source will be equal to the total voltage over the total resistance of the circuit. You get to 7.63 milliamps, right? Then from there, you choose the stage in the simplification which allow you to calculate other branch current. For I5, you calculate using RT3 and 16.5 kilo ohms. So I5 is 3 milliamps. V7 voltage at 4.5 equivalent resistance RT5. So V7 will be 4.5 over the total current multiplied by the 3 current. You go in the revised there, you get your 19.65. You can use alternative methods and you get the same results. Then the next thing will be on ladder networks, right? So a ladder network just looks like a ladder with branches in between. That's all what it means. Nothing so special about that, right? But then you can simplify them. The other types, the R2R ladder networks, where you can use some simple methods of calculating the voltages and the like. But then I hate memorizing stuff. So I'd rather, instead of trying to identify whether there's an R2R or something, just do your calculations as usual. But if you have that patience, you can still go on and try to look at them that way. Then you combine, right? So that's how you work with those kinds of calculations. And you can do whatever you want. You can follow that slowly as you watch the video. Like I said, I don't want to make you remember a few things from the head. So consider the network shown and calculate the indicated quantities. It's still a series parallel combination, combine components in parallel and those in series. Then you calculate the total resistance, the drawing, and the like. You follow this slowly to your own pace when you watch on YouTube, right? Then you can still go on to calculate any other quantities. Method number 2, which again is a bit complex for nothing, I do encourage you to use that. But for me, it seems method 1 would be easier, where you follow everything in your simple logic. So in conclusion, components in networks in parallel, there are 2 common points. Parallel networks have the same voltage across them. You notice a point which is common to 2 or more networks or branches. Current entering a node equals current leaving the same node. Current flowing in a branch is inversely proportional to the distance of that branch. That's all we have for today. We do it when I wanted to, not to miss on the time which is left. Thank you. I think I have to end the class right now. We'll continue with the discussion later. Bye, everyone. My time is up.